Okay, so first I'll do the intuition and then I'll do the math. So it's a geometric sum and it's a whole bunch of points around the unit circle. So we start with e to the minus 2 pi I x0. Let's plot these points. E minus 2 pi I x0. And now we go rz over 2 to the 2L. So the next one we want to plot is y equals 1. So we go some distance around the circle. And let's plot another point. And then we plot another point, another point, another point. We keep on going. And what we get is quite possibly points that are nearly exactly uniformly distributed over the unit circle. Some close to 0 unless what happens is, here was e to the 2 pi I x0. I should divide by 2 to the 2L. And here is e to the 2 pi I e to the minus 2 pi I x0 plus y equals 1 here, r, I forgot z here, z over 2 to the 2L. So unless what happens is when we plot the point, we move around by the angle 2 pi I rz over 2 to the 2L, and suppose this angle is tiny. Well, what happens then is we get points uniformly distributed. Suppose it's tiny enough so that when we add all of these 2 to the L over r points, we get points that are, subtend an arc which doesn't even go all the way around the unit circle. Sum is close to, well, how many points were there? There were 2 to the 2L over r, and they were all pointing in more or less the same direction, so in absolute value. So there's two cases here. If if 2 pi I y r, if 2 pi I rz over 2 to the 2L is close to 1, which means rz over 2 to the 2L is close to an integer. If rz over 2 to the 2L close to integer, and let's call that integer d. So if this is close to an integer, then we get a large probability of seeing this. If it's not close to an integer, we get a tiny probability of seeing it. So now what I'm going to do is actually do the geometric sum. So the geometric sum is 1 minus e to the 2 pi I. We want the last term of the sum. So that's 2 to the 2L rz over 2 to the 2L. No, it's y goes from 1 to 2 to the 2L over R. So the last term you substitute in 2 to the 2 to the 2 to the 2L R over Z. So something like 2 to the 2L over R. And we'll have to take the floor of that times R times Z over 2 to the 2L, which really, because of this floor, could be anywhere on the unit circle. So, but it's always less than 2 in absolute value. And we're dividing that by 1 minus e to the 2 pi I to the 2L over R. No, we leave that term out. RZ over 2 to the 2L. And remember, the sum is really, so we're dividing something by something else, and it's going to be relatively small unless the something else we're dividing is really, really, really close to 0. So this is roughly something of 1 divided by, well, what is this? This is roughly RZ over 2 to the 2L. So the probability of seeing a number Z is roughly RZ over 2 to the 2L squared. Minus D, because D was our integer. So we have D over R is roughly Z over 2 to the 2L. So what our algorithm does is it outputs Z. We know 2 to the 2L, and we need to round it off to something like D over R. And there is a procedure for rounding numbers off to smaller, rounding real numbers off to smaller fractions that is efficient, and it's called continued fractions, and we'll talk about that later. But it's a classical algorithm, so once we get this, we can round it to D over R, and then we found R, which was the period we were looking for.